perfection, as you know, is more a journey than a destination. You can never reach perfection, we can only attempt that. So perfect castings sounds a little difficult to achieve because we know that the rejections are in percentages, not even in parts per million, and so talking about perfect castings does sound very strange. So in this lesson we will look at the philosophy that perfection is not just about quality or rejection but many more things, and we look at from two perspectives. We look at from customer's perspective and foundry perspective. So in this lesson we will look at what are the challenges facing foundries vis-a-vis the requirements of the customers or OEMs, and we also towards the end of this lesson define what is perfect casting and how do you achieve that. So let us start with the requirements of the OEMs or original equipment manufacturers. As you know, there is an increasing trend now to reduce cost, and they try to achieve that by reducing the weight. Now you can do that in two ways. One is you can reduce the wall thickness, make the walls more thin. Second is they can use sophisticated tools to optimize the shape of the casting. So shapes are getting more complex, the walls are getting thinner, and this of course puts some kind of a challenge on the foundries. The second group of requirements is about quality, and it's not just to make sure that the internal quality is free of any defects, but also they want consistent quality and consistent properties, and that's much more difficult to achieve. The third is about time. Not only customers want the initial proven samples fast, I mean used to take weeks and months, now they want it in days, and secondly once a sample is approved they want the regular production to happen in just in time, shop number, the gate number and time and date is given and they have delivered at that point of time. Last but not the least, they also need continuous cost reduction. Initial quotation can be fine, but they expect some percentage reduction year after year after year. So these are the things which customers expect from their suppliers. Now from foundry's point of view, they need to meet these challenges. One is, the biggest challenge is about quality or rejections. We know that even in production foundries the rejections can be as high as 2 to 3%, 5%, but if it's a jobbing foundry, rejections can be as high as 5, 10, maybe even more, 15, 20%. So this is priority number one. Number two is, once they conquer the quality demon, you can say, the next bigger challenge is to achieve good yield. In a large thick steel casting, yield can be as low as 50%, which means you are melting 2 tons of metal to produce 1 ton of good castings. Now this has to be improved because yield directly affects the energy consumption and therefore the cost of the castings. Third is, when they are developing a new part, they need to do a lot of trials on the shop floor. So you do it, you change the methoding, the tooling, put it on the shop floor, cut that, inspect that and see if it's okay. If it's not okay, go back, change the design, tooling and do it again, and each iteration can take a week or more than that. Now if you do 5 or 6 iterations, you have lost 1 to 1.5 months there itself. Now that has to be reduced. Well, it's a loss of productivity, loss of material, energy, other production resources. Other two is cost, we already know, but foundries are also looking at different ways to enhance the value to the customer. They are looking at possibilities that can their experienced methoding engineers go back and help the designers make some changes to part design so these parts have inherently good quality and easy to manufacture at low cost without too much effort on the shop floor, what's called as design for manufacturing. Because it requires foundry knowledge, it's the casting engineers who are best placed to advise designers in this aspect. So these are all the different challenges before foundries to collaborate with their OEMs. Now to meet these requirements of OEMs, foundries do take up a lot of pressures. The two pressures what you see right away is from the customer and from the competition. Now customers, as you've seen, they require quality assurance, they require reliable delivery, initial sample fast, reliable on time, just in time delivery of production parts, and they want continuous cost reduction. And end of that, you cannot say that the customer will buy from the same foundry the moment they find some other foundry who can supply all these criteria or meet all these criteria at a lower cost, they'll shift to him. So foundries can never be guaranteed about business from a particular customer. Now from competition is always eating someone else's lunch, so we have competition not only from within the country or within the cluster, different parts and different countries. They are looking at if they can give better cost, better value or quality or delivery, there is always a issue there, and they can always get the loyalty of a customer shifted to themselves. So these are the two pressures coming on a foundries from the customers and competitors. But there are two other pressures coming in. One is from the resource crunch. Increasingly foundries all over the world, not just in India and China, are facing the problem of skilled manpower. Not just manpower on the shop floor, but also manpower to do methoding, to do analysis, to look at quality. There is a big crunch of manpower there. Second thing is materials are no longer having a steady supply as it used to be earlier. As you can see in the last few months and years, the fluctuation in rates and shifting of suppliers and quantities, it's become a big problem for foundries to maintain a steady supply of incoming raw materials. Energy is becoming an issue in many parts of the country, especially in India. Recently we have many pockets of country where power cuts are affecting foundries, and they're either forced to go for in-house generation or cut production, which is an issue. And finally, technology by itself is an issue, because let's say highly automated molding machines or simulation technology, which we'll see later, these are expensive, and it requires resources, not just hardware but also manpower to run these things properly. On the regulation or government side, you have other pressures coming in. Foundries are required to meet certain safety norms, certain standards in terms of working environment and so on. Not only internal environment but also effect on the external environment in terms of no pollution, in terms of solid effluent, solid, liquid or gaseous effluents, also noise pollution. And we also have our own labor regulations. So these have to be met, and foundries are finding it increasingly difficult to meet these challenges and still offer castings at the right amount, value point. Okay, so let's see a scenario in a typical foundry and how they develop a casting, and what challenges they are coming across and what issues that they need to address at that stage. So let's say a typical scenario in a particular week, a foundry gets 8 inquiries from potential customers. Okay, and the first thing they need to do is to prepare a quotation, and maybe they find out of 8 inquiries, maybe 2 are outside their sphere of capabilities. Maybe the material is not matched, or maybe they want very thin walls which they can't make from their own process. So let's say they prepare only 6 quotations and send it to the customers. Now the key here is speed. Literally the person who sends a initial good quote has a big advantage in terms of perception in the eyes of customer that yes, these guys are capable of doing things fast in time. So speed is the key when you convert from inquiry to quotation. The next step is from quotation you need to start looking at tooling. Let's say you out of 6 quotations you got 4 orders for sample castings. So let's say you select out of those, maybe out of 6 you get 4 because maybe you don't want to take up the other 2 orders, or maybe you got these 4 orders. So you prepare the tooling for them, prepare the patterns and core boxes and so on. And here the big issue and critical issue is the accuracy. The drawing sent by the customer and the tooling which you have prepared, if they have a close match, then everyone is happy. If there is a big difference in geometry or weight, then there is a problem. So accuracy is a key in this step. Next, once you have the tooling ready, you pour the castings and make those parts. Okay, and let's say you have now 4 samples ready, and here of course the issue is, can you get the quality right? Okay, is it free of internal defects, and is the shape okay, are the properties okay? And if you can meet this challenge, and let's say the samples are now sent to the customer, maybe the customer gets samples from other places and maybe he chooses some other suppliers for some parts. So maybe let's say you finally get 2 orders out of the 8 that you initially got the inquiries for. And once the regular order starts, the key issue is reliable on-time delivery. Maintain the quality, but make sure deliveries are on time, right place, right time. Okay, so let's say these 2 orders you start supplying, and then end of the year when you do your balance your books, then you find that okay, one part you made a profit, another part maybe you just about broke even or maybe even made a loss. Okay. So here the issue is, have you been frugal enough in the manufacturing systems that our costs are minimum and then there is sufficient margin to make sure there is a profit and not a loss. So these are the basic scenario or environment in which a foundry operates. Next we look at, we move towards the so-called perfection or perfect casting. How do you define that? So to start doing that, we first talk about conformance and conformance criteria. So we look at three major groups of conformance criteria. The first one is geometry, and that's fairly well understood because you're talking about getting the shape and dimensions right, and this is essentially affected by the tooling design, the pattern and core boxes. The second conformance, which also foundries are very well aware of and they are handling that pretty well, is integrity or internal soundness. Is the casting inherently free of internal defects like cavities and porosity and cracks and hot tears? That is integrity or soundness. And this is affected by three steps in the casting process, which we know: making of the cavity, melting and pouring the metal, and finally letting it solidify in controlled conditions. These three events affect the integrity of a casting. The last one, which is now becoming more and more important, is properties, especially mechanical properties like tensile strength and hardness and fracture toughness. Now these are a function of the composition of the cast metal, but it is more than that. As we see, it is not just composition but also composition interacting with the mold material and the process parameters to give you certain microstructure which affects properties. So these are the conformance criteria. Now how do we achieve them in a foundry? Theoretically we can do it by creating a perfect tooling, perfect cavity of the mold, perfect filling, perfect feeding, and finally getting perfect properties. That is from the supply side. The conformance or ideal conformance means the order and supply are in close match with each other. That's when we say that the conformance is very high. That is the goal of perfect castings. But let's go beyond that. What we defined so far is a goal from the point of view of the customer's point of view. So when you say perfect casting and conformance to the specified requirements of the customer, okay, which essentially means that what I supply, the manufactured part, is very close to or same as the specified or desired part by the customer. That is from the customer's point of view. But we need to say, look at the other side of the coin. The perfection has two sides. The other side is from the foundry's point of view. Here we say, is there a compatibility between what they have to make and what they can make? In other words, between the part design requirements and the process capabilities, is there a good compatibility? If process is not capable of making those requirements of the customer, then inherently there is a gap, and it's very difficult to bridge the gap. Now so it sounds good in practice that perfect casting means you want to get the right quality and get it at as low cost as possible from foundry's point of view. But in theory it sounds okay, but in practice what we need to do is define the limits or the deviation which will be acceptable to say that a particular casting is perfect. What I mean by that is that we say dimensional deviation between the original drawing and the final as cast part. If it's, let's say, plus minus 1 millimeter or 1% of the original drawings, we say it is still can be counted as perfect. Okay. Similarly on the cost side or on the manufacturing yield side, a foundry may say if my yield is more than 80%, which is theoretically, let's say maximum yield I can get is 85, if I get 80%, 85%, I say it is okay from capability point of view. So we need to define those limits within which we can say, we can declare that a particular casting or manufacture of the casting is perfect. Okay. How do we go about doing this whole thing? So we are trying to lay down the broad framework in which we can create theories and principles and rules and eventually software programs which will help casting engineers design perfect castings. So to start with, let us say that a cast part as definition has three elements. To focus on that, let's look at from other way around. We say finally from production point of view, we say a cast part is defined in terms of three elements. We say if the quality is right, if the total cost is okay, and productivity is as desired, we say it is from the production point of view. Now these three depend on the process. what I defined just now, the quality, cost and productivity is the final outcome of a perfect casting, but that is achieved by going one step lower, which is getting a process right. How do you get a process right? I select the right equipment, I make sure my tooling is right, I make sure my process controls are good. There is no point having great equipment if control is completely out of order. But how do we make sure that these are okay and compatible? So I need to go back and look at my part design. If my part material is steel, I can make it only by, let us say, sand casting or investment casting. If it is a thin wall steel casting, I need to go for investment casting. So material, geometry and the quality tolerances not only dimensions but also on the quality. These define a process and process defines my final outcome. So this whole chain of knowledge, you can say, if it can be accumulated and learnt and transmitted, we are in good shape. That is possible by a continuous feedback loop where a production, whatever is produced in a foundry, if the data or knowledge is captured and fed back to designers and they therefore design a part, next time they design an investment casting steel part, they know that wall thickness cannot be below, let us say, 0.8 millimeters for a length of, let us say, 2 or 3 centimeters. Then it will be inherently good quality. If they break that, then we are essentially setting it up for getting poor quality. So this relationship and the knowledge base helps develop this whole framework for perfect castings. So to summarize, what we have learnt in this lesson is that OEM expectations, that is customers of original equipment manufacturers, their expectations for foundries are continuously increasing in terms of quality, deliverability, cost and other aspects we have seen. But foundries on the other hand are also challenged by several pressures as well as a process which is inherently complex because of a large number of parameters and interactions between the parameters. So it is not easy to meet those requirements, and on top of that they have their own problems of crunch in terms of getting the right materials or manpower or various resources like energy. So in this whole scenario we can define perfect castings as one where you get fairly high quality as desired by customer at fairly low cost as desired by the suppliers, and this combination is what we call as perfect castings. Okay, and how do we achieve that? By a good optimization of the design parameters which lead to a selection of the right process to right equipment, and therefore your outcome is going to be good. Okay, and all this requires a lot of continuous capture and reuse of knowledge. In this course we are going to show you some of the knowledge elements which we have captured so far and how to use that for making what we defined perfect cavity creation, perfect filling and perfect feeding of the castings. So we will stop here.